So can you see my slide?
Okay, it's okay now, doctor. Thank you.
Sorry, I cannot hear you. Can you see my slide?
Yes, we can see your slides. Yes, we can see.
Okay. All right. So thank you very much, ladies and gentlemen, for inviting me in this ASEAN conference on additive manufacturing. Let me introduce myself first. My name is Yupiter HP Manurung. I am the director of Smart Manufacturing Research Institute. And my presentation today is actually entitled with the modeling and simulations of metal additive manufacture. So the outline of my presentations will be as follows. At first, I would like to introduce a little bit on our SMRI, Smart Manufacturing Research Institute. And then I'm going to present on this applied modeling and process simulations for metal additive manufacturing. And then followed by the current research at SMRI on metal additive manufacturing. And then last, I'm going to present on these conclusions and outlook. All right, first of all, a brief introductions to SMRI. I would like to actually introduce who we are actually. So we are actually established institute at University of Technology Mara since 2019. But we actually started already with our center last time since 2010. It is so-called the AMTEX, Advanced Manufacturing Technology Excellence Center. And our focus is on this applied research, consultation and certifications, and also professional training. And we have also a website here, and you can contact us also later for any collaborations and so on and so forth. So SMRI consists of 6 units. We have Unit 1, Advanced Virtual and Additive Manufacturing, Transport and Infrastructure, Medical and Pharmaceutical Engineering, Lean Kaizen and Reliability Engineering, Robotic IoT, and also Energy and Oil and Gas. So a little bit on this SMRI with organization chart. We have the me myself as the director, and we have also the unit leaders. So we have also fellows of SMRI, consists of experts from local and international. So we have also sufficient facilities for doing applied research and also for teaching learning. We have good facilities in terms of welding technology and also additive manufacturing. And also we are equipped with the softwares. We have additive manufacturing software, simulation softwares, and so on and so forth. So we have also collaborations with some institutes, local and also international. So we have also we have collaborations with German universities, German companies, Austrian universities, and so on and so forth. Okay. So we also managed to receive some international grants for research, for applied research from Germany and from Austria. So that's all actually a little bit on this our Smart Manufacturing Research Institute. Okay, so we come to the part 2. This is about the applied modeling and process simulations for metal additive manufacturing. So first of all, this is actually this presentation is actually like the sharing of experience what we have done at our Smart Manufacturing Research Institute. First of all is in our institute with regard to metal additive manufacturing, we are doing some sort of the generative design for metal additive manufacturing. You see here the process, the iteration process of the design, from the conventional design into the generative design. So actually there are a lot of examples for generative modeling using generative design. For example, BMW is also doing that kind of the frame of the motorcycle. Airbus is also doing the generative design. We have also here mesostructural femur bone implant. We have also wheel carrier, and NASA interplanetary lander. So we have also another motivating examples, which inspired us to do also this kind of the research. So basically, we develop the generative design model and process simulations. Yeah, if you can see here on the right side, this is our 11 steps of GD and process simulations. Yeah, so starting with the original design, yeah, step 1. Yeah, and then geometrical modeling for GD. Yeah, and then generative design outcomes. Yeah, through this software, yeah, sophisticated softwares. We have also we have collaborated software actually partner, yeah, to do this generative design outcomes. Yeah, and then we have to select the design. Yeah, and then on the step 5 and 6, yeah, we have to do the static stress analysis and also the sculpting process. Yeah, this is like a loop. Yeah, if we are not satisfied with the static stress analysis, yeah, we have to do again the sculpting process. Yeah, and then we decide to the final design. Yeah, and then we do the process simulations. Yeah, so we are at our institute. Yeah, we have we are using some specialized software. Yeah, and then we do the process. Yeah, this is a SLM based process. Yeah, and then on step 10 we have the product testing. Yeah, before we do the step 11, the applications. Yeah, so on the left side, yeah, you can see also the flow chart. Yeah, of the that kind of generative design. Yeah, starting with the design. Yeah, and then preserve the geometries. Yeah, so if I can use the pointer, yes, here. Yeah, so the preserve geometries, and here is we have to define the constraints. Yeah, the parameters constraint. Yeah, whereby this one is software dependent. Yeah, some software are required strut density, yeah, manufacturing constraint, yeah, shape complexity, shape quality, yeah, and symmetrical geometry and cost constraints and so on and so forth. Yeah, other softwares requires only, for example, material selection, yeah, and load and mechanical boundaries. Yeah, and then we can define the stress goal, yeah, or the safety factors. Yeah. So after that, we are doing the executions of the generative design. Yeah. So actually, the generative design is iterative process. Yeah. Here is actually the core of the process of generative design, whereby we are having the rule of algorithm. Yeah. Here. Yeah. By having the source code. Yeah. The rule algorithm can be the machine learning or artificial intelligence, or also the level segment. Okay. Next. Oops. Okay, so before we go to the process simulations, yeah, after the geometrical modeling by using the generative design, yeah, we are doing the, we have to understand a little bit on this process simulations. Yeah, so whereby that the simulations will never replace the physical experiment. Yeah, but it can minimize the cost and trial and error attempts. And the simulations results are never 100% correct. Yeah, because of the input data is approximated, yeah, and the mathematical or geometrical model is idealized, yeah, and also the accuracy is limited by the computer computational power, yeah. So we can see also here the difference between experiment and simulation, yeah. All right. So the challenges of the process simulations, what we have actually facing that these conflicting objectives, yeah. So whereby we would like to have the fast calculations, yeah. So we would like to have the process change, yeah. We would like to have the real physics, yeah, and we would like to have simplifications. Yeah, but this one is the conflicting objectives, yeah. So that at the end of the day, we should have this interdisciplinary sciences, yeah, and then the chain process, yeah, with the lumping and sensitivity analysis, and followed by optimization should be applied, yeah. So and then here also we found out that the faster simulations method, yeah, should be supported by simple empirical analysis, yeah, and also optimization, simplified optimizations actually, if you would like to have the faster simulation. Yeah. All right. So this is the existing simulation fields in the research. Yeah, you see here we are still here in the continuum theories. Yeah, at SMRI. Yeah, so we would love actually to go deeper and deeper. Yeah, up to the discrete dislocations dynamics. Yeah, molecular dynamics and also quantum mechanics. Yeah, but we found out that in industry, the industry would like to have faster results. Yeah. And for industry, this is actually still enough. Yeah, the continuum theories, yeah, to be used, yeah, in the industries. Yeah, of course, a little bit theory can be also a deeper theory can be also we can touch also a little bit on this crystal plasticity, yeah, and so on and so forth. Yeah. So, but at SMRI, yeah. So we have here relevant simulations fields. Yeah. So we are actually focusing on this applied research. Yeah. Whereby we are we are using this simulation type. Yeah. For example, the thermal. Yeah. Thermal simulation type. Yeah. This one is for temperature measurement or prediction. Yeah. And then we have here the mechanical simulation type. Yeah. The objective is for the distortion. Yeah. And then we have also thermomechanical. Yeah, these all are based on this continuum finite element. Yeah, so and the objective is distortion, residual stress, and also grain size. Yeah, so we have done also the thermomechanical metallurgical. Yeah, is also based on the continuum finite element. Yeah, for the objective for investigating the grain size. Yeah, of course we can have the bombastic simulation type, yeah, for example, this microstructure by using the cellular automata, yeah, or phase field, yeah, for the grain structure and texture, yeah, and also discrete dislocation dynamic, yeah, for the deformations or failure crack initiations, yeah. But today, yeah, we are not going to touch this too deep in the theoretical simulation type, yeah. So we are going to discuss on this applied simulation type, yeah, whereby we are going to focus on this thermal, yeah, mechanical, thermomechanical, and also thermomechanical metallurgical. Okay. So at SMRI, we are actually focusing on this, yeah, the applied simulations fields, yeah, for the metal additive manufacturing. You can see also here, yeah. So we have here thermomechanical method on the micro scale. Yeah, and we have also here thermomechanical method on the meso scale. Yeah, here we have inherent strength method, yeah, on the macro, yeah, macro scale. Yeah, so whereby here the method, yeah, so we differentiate between non-lumping, yeah, and also lumping. Yeah, so whereby we have lumping moving, yeah, and also lumping layering here on the TMM meso. Yeah. And for macro, we have only the lumping layering here. Yeah. So if you see here the difference, yeah, between the scale, yeah, the applications, yeah. So to compare between TMM micro, yeah, and TMM meso, and also ISM macro, yeah, you see here the computational time, yeah. This one is very long, yeah. Here is short and shorter, yeah. Moving is short, and layering is shorter, yeah. So on the macro or ISM, that one is very short, yeah. But the level of detail here is high, yeah. Here is low, here is very low actually, yeah. Sorry, it's not very short. So the quality of result is very good here, yeah. Here is good, yeah, to better, yeah. Here is sufficient, yeah. And the required material data here is very high, yeah. Here is high to low, yeah. Here is very low, yeah. So the process parameters, required process parameters, this one is very high, this one is high to low, and this one is very low. So you see here the user, yeah, the user, we found out that this TMM micro, yeah, this is more or less on for the R&D, yeah, research and development, yeah. So for TMM meso, yeah, this one is for R&D and industry, yeah. And here ISM, yeah, industry loves to use this kind of the inherent strength method, yeah, or macro scale, yeah, because the result is very fast, yeah. So you see also here is the simulation result. This one is on the micro base, yeah. So you would like to have the powder size, yeah. So here we are doing actually the lumping. Yeah, we start to use the lumping method here. Yeah, we are not going to have the element size as big as the powder size. Yeah, so here is a bit coarser. Yeah, but the problem is we need to have the calibrations. Yeah, so calibrations is very tedious. Yeah, and very complicated and time and cost intensive. So the best thing is actually for our in the R&D, yeah, and also industry actually, how we can combine the TMM and the ISM, yeah, to get the faster result and faster and accurate result. All right. So this is actually a very common governing equations. Yeah, for the left side is for the TMM here. Yeah, you need this one is the Fourier series. Yeah, so it is very normal, very common. And here is the energy for the conduction, yeah, convection, and radiations. Here is the latent heat. Yeah. So and here is actually for the ISM. Yeah, for the macro scale. Yeah. So we can find a lot of theories on that. Yeah, starting with the Murakawa. I think that one is this professor is from Osaka University. Yeah, from Sonia Johnson, yeah, from the Matteo Bugatti, yeah, on Mr. Hill, yeah. So we found out that this one is actually similar, yeah, all the equations is similar. But yeah, the most important thing is actually in this ISM we need the strain to get the accurate result, yeah. But as I mentioned before, yeah, the calibrations is very tedious, yeah, and cost and time intensive. Yeah. Here at MM on the other side, yeah, we need also calibrations, but on the temperature, yeah, to get the good result. Yeah. Okay. So now we come to the part 3. Now we are going to discuss on the case studies what we have actually conducted at our Smart Manufacturing Research Institute. Yeah. I think we have here 5 case studies. Yeah, but before that, at our SMRI, our focus and equipment, yeah, or infrastructure on metal additive manufacturing. Yeah, so we are using our the Renishaw laser powder bed fusion, yeah, for SLM. Yeah, so we are using robotic welding, yeah, for directed energy deposition WAM. Yeah. So we are using also the optical measurement system GOM and also the normal CMM actually. Yeah, I didn't put here. Yeah, but this one is actually the advanced optical measurement system for 3D scanner. Yeah, GOM Atos. Yeah. So in terms of the software, yeah, we have also here our partner. Yeah. So Hexagon. Yeah, we are using also Simulfect Additive. Yeah. We are using the MSC Mark. Yeah, we are using generative design Apex. Yeah, that one is from the Hexagon softwares. Yeah, MSC software. I mean, yeah. So we have also collaborations with the Altair. Yeah, we are also using the Pin 3D software from Altair Inspire. Yeah. So we are also collaborating with the Autodesk Fusion 360. That one is for 3D for the generative design. Yeah. So and also here, yeah, last but not least, this one we are also using actually open source. Yeah, Elma. Yeah, this one is very sophisticated finite element software. Yeah, a lot of researchers are now more and more using this finite element software, which is open source. Okay, so the first case study is actually we are predicting the distortion substrate distortions. Yeah, so the idea is actually from one industry which would like to use this one-piece substrate and component. Yeah, it means that after the additive manufacturing, they would like to use the whole piece, yeah, with the substrate. Yeah, so we are given the task, yeah, to do the research, yeah, on the distortion prediction. Yeah, so at first we are using the thermomechanical method TMM. Yeah, so the beauty of this research is that the material modeling. Yeah, so here, yeah, we are actually considering the 3 material model here. Yeah, the first one from the database itself. Yeah, from the software database. Yeah. And then from the wire, yeah, you see here from the wire, yeah, we check the chemical compositions of the wire. Yeah, so you see here the filler wire, yeah, it is different. Yeah, database here. Yeah, this is the database. Yeah, and then this is the component. This one is the evolved materials. Here is the evolved materials. Yeah, and here on this from the filler wire. Yeah, so you see here the plasticity model seems to be similar here. Yeah, but it is actually different. Yeah. So you see here also the different compositions, as I mentioned before. Yeah. So we see here also the different distortions. Yeah, the different distortions. So we found out here, yeah, as our conclusions. Yeah, if the material model from the software database, yeah, you see here that the error, the percentage of error, can be up to 20%. Yeah. If you are doing if you're using the material model from the filler wire. You see here up to 8%. Yeah. So and then here material model from the component, from the evolved components, actually evoluted components. So it can be up to 5 to 6%. Yeah. So you see here is the difference. Yeah, of the error. Yeah. Okay. So the case study number 2 is actually the grain size prediction. So it's also by using thermomechanical metallurgical method, yeah, TMMM. Yeah. So why we are using we are investigating the grain size. This one is actually the objective for the our further research, yeah, on the corrosions, yeah, on the hardness value, behavior, yeah, tensile behavior, and also last but not least is on the fatigue strength. Yeah. So we also we have done also some literature review, yeah, on the worm. Yeah. So we found out here, yeah, that the grain, yeah, the grain is actually growing, yeah, from the bottom to the upper side. Yeah. So this is actually our experiment. Yeah. It is also actually look like similar to the past research. Yeah. So this is actually our the results of our experiments of WAM. Yeah. So we started with the bit on plate. Yeah. Experiment. Yeah. And also the sample fabrications. You see here we conducted also the temperature measurement inside. Yeah. So in the bit. Yeah. Temperature measurement inside in the bit. Yeah. So that we can do the calibrations of the temperature. Yeah, as I mentioned before, that the TMM needs the calibrations of the temperature. Yeah, so that we can have the similar temperature between simulations and the experiment. So we found out that, yeah, so the default heat transfer coefficient, for example, yeah, in database we found out that there is a certain value which is normally used, yeah, by the researcher, yeah, but it is not so correct actually. Yeah. So actually we found out that in our experiment here, yeah, that our heat transfer coefficients is more than in database stated. Yeah. Okay, here material verifications. Yeah, we have done also the material verifications, yeah, on the components. Yeah, we are using the arc spectrometer and also STM actually. Yeah. Yeah. So and then we are using the dilatometer, yeah, for investigating the activation energy and also the MO. Yeah. So we have here 4 temperature range, yeah, ranging from 900, 1000, 1100, and 1200. Yeah. So and then we put all of these parameters into our FEM simulations. Yeah, of course, there is not available in any specialized software on this grain size predictions. Yeah, so that we have to develop our own subroutine for that. Yeah. So you see here the general equations, yeah, we are using for the grain growth. It's very simple actually. And one is the first stage of our research on this actually. Yeah. So you see here modified kinetic constant MO and also the activation energy. So we obtain this value from our previous experiment, yeah, by using the dilatometer. Yeah. And then here you see here there are some cases actually. Yeah. Yeah, this one is actually the original equations. Yeah, so in our case that the precipitation is not happen, because the temperature is very fast, yeah, and then we found out that we call it as the free grain growth, yeah. So that here we see that the G limb, yeah, is actually infinite, yeah. So that we can remove this one, yeah, to be this kind of the equations only, yeah. So this ODE should be solved, yeah, by using the numerical approach, yeah. So a lot of numerical approach actually can be used, yeah, for solving these ordinary differential equations, yeah. So we are using the Runge-Kutta fourth order, yeah. So we found out, yeah, that this fourth order is very sufficient, yeah, for that. So you see here the result, yeah, the results of the for example here transfer coefficients, yeah, this one is 2000, yeah, and here is 45 for the metal to air, yeah, metal to environment. This one is metal to metal, yeah. You see here, this is our error percentage, yeah. So you see here by using our subroutine, yeah, we have around 5 to 6% of error percentage if we are for our grain size prediction. Okay, so the case study number 3 is actually for the distortion prediction, yeah, of SLM based turbine lifting bracket using generative design and also TMM here, yeah. You see here our conventional design, yeah, traditional design, yeah. So we have here the load, yeah, which is actually a given, yeah. So that this is a stainless steel 316L, yeah. You see also here the mass is 0.325 kg, yeah. So you see here after the generative design, yeah. So we found out that we can have this weight reductions up to 59%. Yeah. So before we print it by using our Randy Shaw SLM, we are doing first the simulations, yeah, by using a SIMUFX software. You see here we have here distortion and residual stress. I don't know, I cannot play the movie here. Okay. Maybe I have to. Oh yeah, here. Yeah. So by using the SIMUFX, you see here the TMM, yeah, for this 5 bracket, yeah. The computational time is quite actually fast here, 3.5 hours, yeah. So we can predict the distortion and stress. All right. So here, in terms of the distortion, yeah. So we find out that by using this specialized software, yeah, and also the optical measurement, yeah, 3D scanner, yeah. You see here two steps, yeah. The original design with the 3D scan, and here 3D scan and sorry, yeah, and the simulations, yeah. So we you can see here the mean error of distortions, yeah, using FEM, TMM, yeah. It is around 1.85%. Yeah, this is one is actually a very good predictions, yeah, by using the specialized software. Okay. The number 4, yeah, I have here 5 case studies. Yeah, number 4 is actually the distortion predictions on SLM based cylinder, yeah, using combined TMM and ISM, yeah, using the combined thermomechanical method and inherent strain method. Yeah, as I mentioned before, yeah, for the ISM, yeah, we need the calibrations. Yeah, here, yeah, we are actually using the simulations for the calibrations. Yeah, we call it as the virtual calibration test. Yeah, of course, yeah, the geometry of the calibration test here, yeah, can be different. Yeah, so here in our case here, yeah, we selected, yeah, from our own database that this kind of calibrations specimen geometry is very sufficient, yeah, for them. So what kind of the product which will be printed? That one is like a cylinder product, yeah, SLM based, yeah. So this is actually we have taken from the University of Cambridge, yeah, the group of the Professor Davies and Willems, yeah. So they have done this experiment, yeah. They have also published, yeah. So we are doing here actually, yeah, the the virtual calibration test, yeah, and the ISM, yeah, simulations here, yeah. So this is very fast, yeah, actually, yeah. So this is very fast process, yeah. So that you can see also here, yeah, the results, yeah. So this is actually by Prof. Davies, yeah, from Davies from University of Cambridge. You see here the percentage is 5%, yeah. So here combined TMM and ISM, yeah, simulations, yeah, we obtain here 8%, yeah, 8%. Here only TMM. We are also doing the TMM simulations. Yeah, this one is around 4.6%. It is quite similar. Yeah, because the group of University of Cambridge, they are also doing the simulations here. It's around 5%. Yeah. So here the combined TMM and ISM by having this virtual calibration test, you see here is 8%. Yeah. So it can be improved actually. Yeah, it can be, especially on this calibrated geometry. Yeah. So that we don't need this calibration. So this one, believe me, that one is very tedious. Yeah, very. This one is actually the parts which we have done by ourselves. Yeah. So we have to print. Yeah, and then we have to cut. Yeah, we have to cut the substrate. Yeah, and then we have to cut by use for the on the support structure. Yeah, and then we have to measure. Yeah, we have to measure. Here is actually the step. Yeah, the step. Yeah, by having this our combined TMM and ISM by having the virtual calibration test. Yeah, here is the mesoscale simulations on simplified calibration specimen. Yeah, and then we measure the maximum distortion. Yeah, and then we are having the inherent strain tensors. Yeah, and then we optimize. Yeah, by having optimization method. Yeah, for example, Nelder-Mead, yeah, method. Yeah, we can use also here. Yeah, and then we can use the macro scale simulations, yeah, for predicting the distortions. Yeah, so you see here also on the computational time, yeah, from University of Cambridge, we don't have any report on that. Yeah, so here you see here 63 minutes, yeah, by using this virtual calibration test. Yeah, and here is 130 minutes, yeah, for this kind of small spacing. Yeah, you see also here, yeah, so meaning that the tendency, yeah, the mesoscale here is mesoscale. Yeah, so the blue one is the meso and microscale TMM and SM. You see here, yeah, so it can be improved actually. Yeah, so this kind of method, a simulation method. Okay. So the last case study in our institute, yeah, is we again, yeah, we would like to have the FEM numerical simulations, which is easy, fast, and it can show the similar results with the conventional method. Yeah. So here is we are investigating the effect of the lumping strategy. Yeah. On the distortion, stress, and computational time. Yeah. What is actually the lumping? It's actually it's a compiling of several bodies of elements, yeah, into the single entity actually. Yeah. So meaning that if we have some more than one layers and we consider as a one, yeah, and we would like to maintain actually the same dimensions. Yeah. Here, yeah. For example, this one is our own example. Yeah. And the boundary conditions. So this is this kind of lumping strategy can be used in the additive manufacturing and also the multiple layer or multi-pass welding. So here we define into two. Yeah, we differentiate into two. The first one is the lumping layering, we call it. Yeah, we are using this this theory, yeah, from Mr. Lee, Chow, and Jingfu. Yeah, so this one is lumping the whole one layer. Yeah, the whole one layer, yeah, by having this kind of the equations here. Yeah, so this is, we call it as the lumping layer. The other one is the lumping moving. Yeah, so this is by having moving element. Yeah, but this moving element is actually compiled is compiled from the more than one elements. Yeah, so but here, yeah, the configuration is different. Yeah, we have to do the lumping number here. Yeah, so this is also based on the work or research by Professor Lindgren. So this is the results of the lumping layering. You see here, yeah, the lumping layering, the whole lumping. Yeah, so you can do the here. Yeah, this is the normal one. Yeah, the normal one. Yeah, so you see here. Yeah. So maybe I can make it faster here. Yeah. So here is, you see here, yeah. You see this one is 175 per second. There's only 28 seconds. And you see here is a faster 5.85 times faster. Yeah. So this is on this. Sorry, this one is lumping. This one is, sorry, that one is a lumping layering also. This one is the distortion. Yeah. So the distortion is 0.102. Yeah. Here is 0.084. Yeah. You see here. Yeah. The distortions is also. Yeah. We can see that the tendency is there. Yeah. So the stress, the maximum stress. Yeah. This one. Yeah. Is quite big actually. Yeah. Between the normal one to the lumping one. So if we see the lumping moving, here is the lumping moving. Yeah, so here is the normal one and the conventional one. So here is the lumping moving, but it's also very fast here. Yeah, 40 seconds. Yeah, this is a little bit slower than the lumping layering. Yeah, so we see the distortions. Yeah, the maximum distortions 102. Here is 1.7. Yeah, it's quite actually different. Yeah, but the tendency is there. Yeah, and here is quite good actually the stress. Yeah, you see here the maximum stress. Yeah, so it can be also improved here. Yeah, so this is actually on the lumping moving. Yeah, so 822 MPa, and here on the right side is 804 MPa. Yeah, so that's all actually our case studies on the applied modeling and simulation. Yeah, so I come to the last part on the conclusions and the outlooks. Yeah, so at first is the material modeling. Yeah, the effect of the influence of the material modeling is very important actually. Yeah, so we can see here the error if we use the properties from a database. Yeah, the error can be up to 20%. Yeah. So if we use the modeling from the feedstock, for example, on the powder or on the wire, yeah, you see here the error can be up to 10%. Yeah, but if we use the involved components, yeah, the material compositions, for example, yeah, it can be more can reach up to 5% only. So his source model and temperature calibrations are required here. Yeah. So for example, here the transfer coefficient metal to metal in our case is between 2,000 to 3,500. Yeah. So default in the software, yeah, I think mostly is 1,000 something like that. Yeah. And also the metal heat transfer coefficient metal to air. Yeah. This is around 40 to 100 watt. Yeah. In our cases. Yeah. So combined TMN and ISM is a very potential approach, yeah, which can save time and cost. Yeah. So the virtual calibration test, yeah, should have a database, yeah, for determining the suitable calibration geometry. For example, you have another geometry on your product. Yeah, we have to define the suitable calibration geometry. Yeah, so that we can have the good accuracy, yeah, of mechanical responses. So this is actually the future. Yeah, we are also doing this kind of method. Yeah, so the probabilistic FEM by using the Monte Carlo method, for example. Yeah, we are not using the very complicated theory. Yeah, Monte Carlo is for us is very enough. Yeah, to replicate the actual process actually. Yeah. So and also the intelligent FEM. Yeah. So by using the artificial neural network. Yeah. So these two are in our research right now. Yeah. We consider this one as the future for the applied process simulation. Yeah. So last but not least, yeah, the lumping method, yeah, can save the pre-processing effort and computational time, yeah, by having good results, yeah, using conventional method, comparing to the conventional. Okay, so that's all from my side. Yeah, so we welcome academic and also industrial collaborations to SMRI. Yeah, if you would like to contact us, yeah, you can see also our website here. Yeah, we have also email here. Yeah, and also we have a LinkedIn. Yeah, you can check at our SMRI UiTM or my personal LinkedIn. Yeah. So that's all from my side.